I just started recording. Okay, right. Right, just to make sure that we are on the same page. So I am using this textbook here, Engineering Science N3, by MJJ van Rensburg. That's the textbook I'm using. Right, Module 1. In fact, Module 1 on all the textbooks for Engineering Science N3 is the same. Right, the modules, how the modules are arranged, regardless of the textbook, is the same. Right, so now as far as Module 1, we covered the kinematics part of Module 1. So that is motion, where we look at quantities that are involved in, what is this thing? Motion graphs. So your distance, displacement, speed, velocity, acceleration. Right, we covered that. Then we looked at forces. Under forces, we looked at Newton's laws of motion as well as the application thereof. We covered this as well. I gave you these activities. I also gave you, I believe, past question papers. Is that correct? Did I send you guys past exam questions in the group?
I don't remember if you did.
Right. I believe I did though. Okay, I'll check my notes just now. We covered all of this. Right. All of this is under forces. Um, Work done, energy and power. Right. We covered all of that. I don't know if you remember, but I said as far as work done by torque, that I said we are going to cover near the end of the trimester. Right. So we didn't cover this. This we will do later. And then momentum, I said there won't be any calculations on momentum in the test. Right. It's just the theory. Right. So you're just gonna go through the theory on momentum. That's and then this we have to do as well. Belt drives. Right. So the belt drives we are going to do now. We are going to look at one exercise which is similar to the one that is going to be in your test. All right. So again, are there any questions regarding what we have covered so far? So kinematics, I think that part is fine. Forces, work done, energy and power. Right. We looked at objects that are moving along the horizontal plane, objects moving along the vertical plane, and objects moving along the inclined plane. So you can expect all of that in the test for sure. Dynamics. Let's see. All right. So I did cover some of the questions from past exam papers. Okay. This was from past exam papers as well. Yeah. Right. So before we go through belt drives, are there any questions regarding anything on kinematics, anything on dynamics? No questions.
Yeah, no questions, sir.
All right. Okay. Let us look at belt drives. All right. So let us look at belt drives. Now, for engineering science, we don't necessarily cover the whole of belt drives, right? This under our syllabus for engineering science N3, we don't cover the entirety of belt drives, right? We only look at a few concepts under belt drives, right? Now, under belt drives, this is what we are going to look at. So, say you have two pulleys. Now, Belt drives essentially falls under mechanical drives, right? You get different mechanical drives. The most typical ones being belt drives, gear drives, as well as chain drives, right? So the concepts we use under all those mechanical drives is essentially the same, right? In N3 though, we only under mechanical drives we only look at um, belt drives, right? Now with belt drives make use of pulleys, right? So you would get, for instance, two pulleys, right? Depending on if it is a simple or compound mechanical drive, or let's say belt drive specific. Simple or compound belt drive, right? So a simple belt drive is where essentially you just have two pulleys that are fitted with a belt or that are connected with a belt. Uh, let's do this. All right, so you have two pulleys that are essentially fitted with a belt. So the blue line represents a belt. All right. So a simple belt drive is one where you essentially have two pulleys, right? And each pulley is fitted with its own shaft. Right. So you'd find that maybe the input shaft is fitted onto the smaller pulley and the output shaft is fitted onto the bigger pulley. Right. So what mechanical drives do essentially, right, is transmit they transmit power. Right. We use mechanical drives to transmit power. Right. So depending on um, what you need the mechanical drive for, right? You then in your design decide if, based on what you need the mechanical drive for, if you're going to use a belt drive, or you're going to use a gear drive, or you're going to use a chain drive, right? Either way though, what is this? All mechanical drives, right? They transmit power, right? So this one, a belt drive, transmits power using two pulleys, right, connected with a belt. Right, two pulleys connected with a belt, right, or let's say pulleys that are connected with a belt. Right, now on the belt, right, so essentially the belt wraps around the pulleys, right? The belt wraps around the pulleys, and then on one side, right, one side of the belt we refer to as T1, and the other side we refer to as T2, where the T1 side of the belt is the tight side, right? That is the side of the belt that experiences or that is subjected to the most stress. That's the tight side of the belt. And then T2 we refer to as the slack side, right? So you have T1, or the T1 side of the belt, which is referred to as the tight side. So the tight side is T1, and then the slack side is the T2. Right. Now, at this level, our tension ratios, we only get to look at what is this? We only get to look at flat belts. Right? We get different types of belts. Right? You get flat belts. You get V belts. Right? But on our syllabus, we only get to look at flat belts. Right? Now, as far as flat belts, we use what we call tension ratios. The tension ratio of a flat belt is T1 over T2 is equal to E to the exponent mu theta. Right, where T1 is the tight side, T2 is the slack side, and then mu is the coefficient of friction. Right, coefficient of friction is dimensionless, doesn't have dimensions. Right, so meaning it doesn't have any units of measurement. Right, it's dimensionless, and then theta is known as the angle of rep. Right, now the angle of rep must be in radians. Right, in linear motion we use degrees, but in angular motion, right, we use radians. Right, that is the angle that is formed. So the angle of rep is the angle that is formed, right, when the belt wraps around either of the pulleys. Hence the name angle of rep. Right, now again, at this level, we don't necessarily expect you guys to be able to convert from degrees to radians, though just for interest's sake, if the angle, for instance, that you've been given of the angle of rep is in degrees, you must divide it by 57,3, right, to convert it to radians. Right, but this we'll look at more in N4 when you guys do Meccano techniques. Right, at this level, now if you look at our tension ratio here, right, there is the left-hand side and there is the right-hand side of the formula. At this level, you are normally given, right, this side of the ratio, meaning they would say maybe say T1 is 2 times T2, right? T1 is 2 times, this is just for as an example, right? They would say T1 is 2 times T2, right? If you look here, if you were to divide by 2 both sides, by T2 both sides, right, that cancels, meaning that T1 over T2 is equal to 2, which essentially means that they've already worked out the right-hand side of the formula for you. All right, so the right-hand side of the formula is normally given to you guys.
Yeah, that's nice.
Right, the right-hand side is normally given to you, meaningly, I'm yet to see questions where you are given. Right, let me see this one. Right, you are. I've hardly seen any questions where, in fact, I haven't seen any questions where you are given the coefficient of friction and you are given the angle of wrap, and you have to work this out on your own. Right? They normally give you the tension ratio, as in the right hand side of this tension ratio formula. Right? You just have to be careful as to how they've given it to you. Are we clear?
Yes, sir. Yes.
Right? But like I'm saying, because this is included in the syllabus, that is why I'm teaching you how to convert from degrees to radians. So that is to say, if you've been given the angle of wrap in degrees, right, substituting it here, you must substitute it in radians. So to convert from degrees to radians, right, you take the angle that has been given to you in degrees and you divide it by 57.3, and what you get there will be the angle of wrap in radians, and that is what you substitute here. So meaningly, if the angle of wrap, for instance, is say 90 degrees, not 90 degrees, say 120, right? You've been given the angle of wrap as 120 degrees, right? You have to take this and divide it by 57.3, and what you get here will be in radians, right? And that is what you take and substitute there. Am I making sense here?
Yes.
Right. But again, for the most part, right, this part is worked out for you. Right, the way they give you the tension ratio, they essentially have worked out the right hand side of the formula. Right. So that's T1 and T2. That's the tension ratio. Right. Now, before, or maybe let me jump into how we calculate the power. Right. Remember, I said all mechanical drives are used to transmit power, right, including belt drives. So we use belt drives to essentially transmit power from one shaft to the next, right, through the use of pulleys. Now, as far as how you calculate the power transmission or the power transmitted is, the power transmitted is equal to effective. Maybe let me do this rather. So effective tension times the circumferential velocity, where the P is equal to the power transmitted by the belt. This will be in watts. TE is the effective tension. It's just like all your tensions, this is in newtons. Right. Also, the effective tension is equal to T1 minus T2. All right. So sometimes they give you the value of the effective tension. Right. Sometimes you have to work out T1 and T2. Then once you have T1 or T2, or if you've been given T1 and T2, to get the effective tension is equal to T1 minus T2. And then V. Now V can be referred to in a number of ways. As they can call it the speed of the belt or belt speed. But the right term for it actually is, let's say, circumferential velocity. Right? Let's say, or belt speed, because sometimes they refer to, in fact, in most cases, they refer to this as belt speed. Right? This will be in meters per second. Right? So this here, right, is the circumferential velocity of the pulleys, or the circumferential velocities of the belt, or belt speed. Right? That will be in meters per second. This here is equal to pi times the diameter of the pulley times the rotational frequency of the pulley. Right? So the D stands for the diameter of the pulley, right? And then the N stands for rotational frequency, right? So let's say D is diameter of the pulley, right? Whichever pulley, right? Be it the small one or the bigger one. This has to be in meters. And then N is the rotational frequency of the pulley. Right, now N is revs per minute or revs per second. In fact, this has to be revs per second, right? But it can be given as revs per minute, right? If it has been given as revs per minute, you have to convert it to revs per second, right? So revs per minute, right? If it has been given to you as RPMs, RPM stands for revs per minute, right? You have to convert it from this to this, right? In substituting it in this formula. Now, the way you do that is you obviously have to convert the minutes to seconds, right? 1 minute equals 60 seconds. So this, converting this from revs per minute to revs per second essentially means that. Right, so you have to divide whatever value you have here by 60 to convert from revs per minute to revs per second. All right, so essentially, if V is equal to pi times D times N, essentially what this means is that if this has been given to you as revs per minute, then it means you have to divide this by 60. Right, dividing this by 60 essentially converts the rotational frequency from revs per minute to revs per second. But only if this has been given to you as revs per minute. If it has been given to you as revs per second, then you obviously don't need to do that. Are we clear?
Yes, yeah.
All right. Right. Now, as far as which diameter or which rotational frequency you substitute here, right? You have two pulleys, right? Both pulleys have a diameter, right? Both pulleys have their own. Each of the pulleys has its own rotational frequency, right? So here, right, if you're going to calculate the belt speed or the circumferential velocity, if you use the diameter of the small pulley, then you have to use the rotational frequency of the small pulley, right? And then if you use the diameter of the bigger pulley or the large pulley, then you have to use the rotational frequency of the large pulley. Right? So that is to say that these two must correspond. If this is for the small pulley, that's for the small pulley. And then if this is for the bigger pulley, then this also has to be of the bigger pulley. These two must always correspond. Meaningly, you cannot use the diameter of the small pulley, but use the rotational frequency of the bigger pulley. Right? Obviously, those two won't correspond because you will essentially be using two quantities. Right? You'll be using two quantities of two different pulleys. Right? So for this to for this to be correct, right, you have to use the diameter you use here. Right? So if it's of the small pulley, right, then you have to use the rotational frequency of the smaller pulley. Right? These two must always correspond. Am I making sense here?
Yes.
Right. So that is how you calculate the power transmitted. Power transmitted is equal to effective tension. Effective tension is equal to T1 minus T2. So this can be rewritten as P is equal to effective tension, which is T1 minus T2 times V. Right. And then V is equal to pi dl. Right. So this can also be let's say here, so this times that is T1 minus T2 times pi times d times n. But this can be rewritten as that. Right. Right. Yes. So that's the curvature velocity. Right. That's the curvature velocity. Right. That's the curvature velocity of this one. Right. Now this is the case for all mechanical drives that use drives that are circular in shape. Right. For instance, the belt drive uses pulleys. Pulleys are circular in shape. Right. Gear drives uses gears. Gears are circular in shape. And then chain drives use sprockets. Sprockets are circular in shape. Right. So for mechanical drives that use drives that are circular in shape, right, the curvature velocities of the drives that we are using, right, is the same. So that is to say, for belt drives, the curvature velocity of this pulley will be equal to the curvature velocity of this pulley. For gear drives, right, the two gears that are responsible for transmitting the power, their curvature velocities will be the same. Similarly with sprockets, right? Sprockets, not sprockets, chain drives. Chain drives use sprockets, right? And the two sprockets are connected with a chain, right? And the curvature velocity of the two sprockets that are connected with the chain will also be equal. So that is to say, if we take this pulley as 1 and take this pulley as 2, right? V1 and you have V2. If the curvature velocities of the two pulleys is the same, it means V1 is equal to V2. Right? V1 is equal to V2. What does that mean essentially? Right? The formula for calculating V in general is pi times, I'm going to use the small letter d for the smaller pulley, times, or let's just say, just call this D1 times N1, right, is equal to pi times D2 times N2, right? So you see how these must always correspond. If this is D1, then that must be N1. If that's D2, then that must be N2 as well. Right? If V1 is equal to V2, then this is the relationship we get. Right? And then mathematically, because these are equal, those two will cancel each other out, essentially meaning that D1 times N1 is equal to D2 times N2. Right? And we can use this relationship to calculate any one of these quantities. Like for instance, if you've been given the diameter of the small pulley and you've been given the rotational frequency of the small pulley, you are given also the diameter of a larger pulley, and then you are asked to calculate the rotational frequency of the larger pulley, then you can use this relationship to calculate that. Any questions? Any questions?
No, sir. No.
All right. Okay. Let us look at this exercise. So let us look at this exercise. Right. So let's write down our given data. A flat belt fits around a pulley which has a diameter of 0.45 meters. The belt has a speed of 17.6 meters per second and transmits 9 newtons per millimeter belt width. Right. The effective pull in the belt speed is 423 newtons, and the belt has a width of 0.18 meters. Right. Now let's write down what we've been given. So a flat belt fits around a pulley which has a diameter. So we've been given the diameter of the one pulley, which is 0.45 meters. Right. The belt has a speed. So we've been given the belt speed or curvature velocity. So V is equal to 17.6 meters per second and transmits 9 newtons per millimeter belt width. Now, how they've put this is a bit flawed, right? But the belt has a speed of this and transmits 9 newtons per millimeter of belt width. Right. Now, if they've given you a tension, right? If they've given you a tension, and the way they've given you the tension is in terms of the tension per millimeter of belt width, right? You can take that tension as T1, right? And the reason why I'm saying how they've put it here is a bit flawed is because nothing from the statements indicates that this tension is for T1 or this tension is for T2, right? How they should have put it at least is they should have said the maximum tension, right, that the belt transmits, or the maximum tension on the belt is 9 newtons per millimeter belt width. Right, that is the right way of putting it, because as much as we understand that the belt has two sides to it. One side of the belt is the slack side, the other side is the tight side. And we know that the side of the belt that experiences the most tension or that is subjected to the most stress, right, is the T1 side of the belt. Hence, they had to indicate it like that. But they did not. Hence, I'm saying if the tension has been given, right, in this format, always take it as T1, right? We actually, this is beyond the scope of engineering science N3, but we actually call it Tmax, right? It is actually called Tmax, right? And then Tmax is equal to T1, right? But because this is not in a syllabus, we are just going to call it T1. Right, so we're going to call it T1. So the T1 here is 9 newtons per millimeter of belt width, right? And then the effective pull in the belt, so the effective, right? So the most important term here is effective. The effective pull in the belt speed is this, right? So effective pull is effective tension. So they've also given us TE. The effective tension is 423 newtons. All right. Also, this one is a bit flawed because I have no idea what the relation, why they made a relation between tension and belt speed. Right. But again, you, if the statement is flawed in the way that they've put it, right, you have to look out for keywords, and the keyword here is effective. Right. We know that as far as effective tension, right, or any effective pull, right, we know they're referring to the effective tension. Right, so the effective tension here essentially is the 423 newtons, and they say, and the belt has a width, so we've been given the width of the belt, which is 0.18 meters. Right, so that is all that we've been given. Now we look at questions. This is 1.3.1. Right. Calculate the power transmitted by the belt in kilowatts. Right. They want us to calculate the power being transmitted by the belt in kilowatts. Right. The power transmitted, we know, is equal to the effective tension times the belt speed or circumferential velocity. Right. We've been given the effective tension. We've also been given the belt speed. So this is going to be a matter of just substituting. This is 423 times V, which is 17,6. I don't have a calculator here with me. So just calculate what this is equal to. All right, what is 423 times 17,6?
Sir, it is 4,448.8.
4,400 then?
Sorry, no, 7,448.
Okay, 7,448, comma. 3 decimal
No,
places.
it's sorry. It said 7,444.8.
Oh, 44.8. All right, so there's only 0.8.
Yes.
There's no more numbers after the 8.
No.
All right. But just remember to always round off to 3 decimal places. Now, this answer is in watts, right? But here they indicated to us that we have to write our answers in kilowatts, right? So to convert from watts to kilowatts, you simply divide by 1,000. Right? Dividing by 1,000 essentially means moving the comma backwards 3 times. Right? So you move the comma by the number of zeros. Right? In 1,000, there's 3 zeros. So you move this by 3 zeros. I mean by 4 numbers. 1, 2, 3. Meaning that this here is 7,445 kilowatts. Right? On your calculators, you can simply use the engineering notation. Right? You can simply use engineering notation, right, to get what the answer is in kilowatts. Right? If you don't know how to use the engineering notation, right, from watts to kilowatts, you divide by 1,000. From kilowatts to watts, you multiply by 1,000. Are we clear?
Yes, yes.
Right. It's very important that you follow, right, the instruction that you've been given. Right. So meaningly, even though that this is correct, right, if you leave your answers here, right, you are going to lose a mark because you didn't express the answer, right, the way you were told to express it, which is in kilowatts. Right. From watts to kilowatts, divide by 1,000. From kilowatts to watts, you multiply by 1,000. Are we clear?
Yes.
All right. Now let's look at 1.3.2. The question is to calculate the tight side of the force. Right. So you see how, or you see why I'm saying our syllabus is a bit short, right? Because in the syllabus, we do not necessarily teach you what Tmax is, right? But if you look at the question, right, the question suggests that we don't necessarily have T1. We actually have Tmax. Do you see what I'm saying? Because they're asking us to calculate T1. Right? And the reason why they're asking us to calculate T1 is because the tension we've been given here, right, is not expressed as newtons, but it is newtons per millimeter of belt width, which is Tmax. So the right way of doing this, right, was, like I said, was to call this Tmax, and then to get T1, T1 is equal to Tmax. Right, and then it depends how Tmax has been expressed. Right, if Tmax has been expressed as newtons, then you use it exactly as it is. And then if Tmax has been expressed the way it has been here, right, then you have to multiply this by the width of the belt. So essentially what I'm saying here is to get T1, right, T1 will be the tension we've been given. So essentially Tmax times the width of the belt. So this would be the 9 newtons. So the 9 times the width of the belt. Now, how this has been given to us is 9 newtons per millimeter of belt width. Right, so that is to say, when substituting the width, right, for this width to cancel these millimeters, or to get rid of the millimeters, it means we have to substitute our width as millimeters. Right. So remember here, this is in newtons per millimeter. Right. Now I'm saying in order to get rid of these millimeters, we need to substitute the width here, in millimeters. Am I making sense here?
Yes, yes.
Right. So the width of the belt has been given to us is meters, in meters, right? Because of how this is given to us, for us to get rid of this, we have to substitute the width in millimeters. So now we have to convert the belt width from meters to millimeters. Right? To convert from meters to millimeters, you multiply by 1,000. Right? To convert from millimeters to meters, you divide by 1,000. So seeing that we are converting from meters to millimeters, we are going to multiply by 1,000. So what is 0.18 times 1,000?
Well, sir, it's written as 180 millimeters.
Yes, it's 180. All right, so this will be 180 millimeters. That way, this and that is able to cancel each other. Now, what is 9 times 180?
It's 1,620.
No commas. All right, no
No.
commas. Newtons. Right, and this here then becomes your T1. All right. Right. Now let's look at 1.3.3. They want us to calculate the pulley speed in revs per second. Right. They want us to calculate the pulley speed in revs per second. Right. The quantity that is calculated or that is expressed in revs per second is the N. Right. So when they say calculate the pulley speed in revs per second, essentially they mean they want us to calculate the rotational frequency of this pulley. Right. Now, as far as V, we know V is equal to pi times D times N. Right. Here we've been given the velocity. We have the diameter of the what is this thing? We have the diameter of the pulley, right? And they want us to calculate the pulley's rotational frequency, right? V is 17,6. This is 17,6 is equal to pi times D. D is 0.45 meters, right, times N, right? So to get N, we must make N the subject of the formula here. To make N the subject of the formula, it means you need to get rid of this. The way you get rid of this is by dividing both sides. Hence, you'll be left with pi times 0.45 as the denominator. And then the numerator is 17,6. Right. And what do you get here? What is 17,6 divided by 0.45 pi?
Sir, so what I got is 12.449, but then you can round it up to 12.45.
What's the number after the 9 here?
At the 9, it is a 4.
So you can round it up to 449. All right. Only if the number after the 9 was 5 and above, then you would round it up to 2 decimal places. Well, essentially not 2 decimal places, but What I mean is, if the number after the 9 was 5 and above, only then would you say that is equal to 2,450, right? But because the number after the 9 is less than 5, right, then this is how you round it off. Right. Remember to always round off to 3 decimal places. This is in revs per second. Right. Or you can just use, you can simply use R for revs per second. Right. Now, just for interest sake, had they asked us to calculate the pulley speed in revs per minute, right? So if they wanted us, or if we were instructed to express this in revs per minute, then what you were going to do is you still have V is equal to pi times D times N, right? And then you divide this by 60. Right, remember that dividing this by 60 means that this is in revs per minute. And then from here, you then substitute. Right, whatever answer you get though from this equation will be in revs per minute. Right, so we took this approach. Right, we didn't divide by 60 because they wanted us to express this as revs per second. Right, but if they wanted us to express this as revs per minute, then you divide the formula by 60, thus making this, right, after substituting here and making n the subject of the formula, whatever you get will be in revs per minute. Are we clear?
Yes, sir.
All right. Right. Any questions? Right. In essence, that is what you can expect as far as belt drives. Sounded like someone was saying something.
So are they only going to offer us one pulley rather than two?
Second?
Are they rather going to offer us just one pulley rather than two pulleys? So you have to calculate one and then the other one as well.
It would depend on the information you've been given. So on this one, they just specified one pulley, right?
Yes.
And based on the questions, right, related to the problem statements, right, we didn't necessarily need the information of the second pulley anyway. But there are going to be occasions where you are required to say calculate either the diameter or the rotational frequency of the other pulley. Right. The most important thing here is that you understand that you have this relationship, and you can use this relationship to calculate any one of these quantities.
It just replies on the correct value.
Second?
Thank you. No, I'll say the same. Thank you, sir.
Okay. Any more questions?
I don't think anything, sir.
All right. If that's it, then I guess we are fine. At this point, I would expect that people are fine with kinematics as well as dynamics. But you've had more than enough time to go through that. All right, so you can use today and tomorrow to go through this question again. All right, try it out on your own. I'll send this in the group. All right, but try this on your own, and then perhaps look at some exercises on your textbooks as well. All right, to prepare for the test. All right, as far as momentum, make sure you understand what momentum is. Also understand the conservation of momentum, but there won't be any calculations on momentum. Right, we will cover that after the first assessment. Right, so I'll do a couple of videos on momentum before we move on to forces. Right, moving forward, I'll be doing a lot of content. Right, so be ready to be very busy, right, in the next 2 weeks. Right, our next session must be soon, where we are going to look at the test. Right, or maybe I'll see, maybe we'll either have a session or I'll record myself doing the questions on the test and I'll upload it on my channel and you can go through it on your own after the test, so that in our next session, right, we can discuss any questions you might have regarding the test after you have watched the video of me going through the test, and then we can discuss what we are going to look at next. All right, the next module though will be forces. Right, you are going to look at forces, then we're going to look at beams, then friction. Yeah.
Okay.
Right, so I'll also draft the assessment plan for the 8-week test, so you guys are fully aware of what to expect in the second assessment. Are any one of you guys doing any other subjects except engineering science and 3?
I am.
Which other subjects are you doing?
I'm doing structural steel drawings N3.
Okay. Okay. Okay, I'll check the timetable to see when you are writing that.
I'm writing that the Wednesday. So Tuesday and Wednesday I'm busy.
Okay. Okay. Yeah, because I thought we could squeeze in a session on Wednesday, but if you are writing, then that will be fair. Okay. What I'll do is.
No, we sorry sir, we can do it because I'm writing on that day, so the night I'll be free, so we can continue.
Oh, so you're writing on campus.
That's correct.
All right. So on Wednesday we are going to squeeze in a session. We are going to squeeze in a session on Wednesday. Right, at 6 p.m.
I have just one question. Can I?
Mhm.
Doing exercises 1.1 until 1.4, should that be okay to prepare us for the test on Tuesday?
Let's see. 1.1 to 1.4.
Yeah, all the activities. I'm talking about the full activities.
Yes. Because 1.5 is based on work done by talk. We didn't cover that, so no need to do this one. No need to do 1.6 as well. Yes. So
Okay.
perhaps you can do 1 point. What is this? Yeah, 1.7. Maybe just select a few there.
Can you post one because we don't have the same textbook as what you're using.
All right, I'm gonna take pictures of this
Okay.
and send it in the group.
Okay, cool.
But to answer your question, yes, activities 1.1 to 1.4. Right, they should be enough. Right, of course, including the videos I sent on those units.
Okay.
Right.
Thank you very much.
Also the theory I covered on those videos. Make sure you understand it. Nah. Right. Right. As from this week, right, we'll be moving a bit quicker now. I only included the first module for the first test because of how things happened. The registration was late. Also, module 1 is very long. Right. So, not to put too much pressure on you guys in the beginning. That's why I decided to only include module 1 because module 1 is very long.
Sorry, sir.
Yes.
Is the second assessment date still the same?
Sorry.
Is the second assessment date still the same?
I only heard assessment date.
Yeah, is it still the same as it was?
Yes, I think it's Tuesday.
Okay.
Still Tuesday.
The second one, the eighth week, is it still going to be the same?
Okay, so that's I will confirm. Normally, the 8th week we do not move though, so that still should be the same. Also, you were asking for the 8th week one.
Yes.
Yeah, the 8th week we cannot move the 8th week test. Yeah, so this one is Tuesday. The 8th week remains the same.
Yeah, that's why you're saying we're gonna do a lot of work.
Yes.
Okay.
But even with that, it's not going to be too much work. For instance, forces is not too long. It's a short module, so that shouldn't be a problem. Moments, okay, maybe moments can be a bit tricky, can be a tricky one, right? But I believe based on how I teach the module, you should be fine there as well. And then friction is similar to what we covered in module 1 under forces, right? Because with friction, we are essentially still applying Newton's laws of motion. Right? The only difference really is that under friction, we always assume that the object we are looking at is moving at constant velocity. Right? If it is moving, then it will be moving at constant velocity. Right? For friction, under our syllabus, we always assume that the velocity is constant. Right? Meaning that F net is equal to 0. Right? Meaningly, the problems we look at always, how can I put this? The problems that we look at under friction are always under equilibrium, right? Be it static or dynamic equilibrium. That's what I mean. Right. So based on the fact that we've already looked at objects on horizontal planes, objects on inclined planes, that shouldn't be a problem. Right? Friction shouldn't be a problem. It's very closely related. In fact, it's the same because we are applying conditions of equilibrium there as well. Right. I just need to decide if I'm going to squeeze in a bit of heat as well. Right. But all of this I will decide this week. Right. One thing for sure though, module 3 will be there. So module 3 is forces. Right. One thing for sure, module 3 will be there. That's forces. Moments, module 2 will be there. Right. Under moments, right, it'll only be beams. Right. Laminars we'll look at later in the trimester. Right. Beams will be there. So forces definitely be there. Moments will be there. Right. Friction will also be there. So I'm saying I'm yet to decide if I'm going to include a bit of heat as well. Are we clear?
Yes, sir.
Right. If there are no more questions, all the best for Tuesday. Right. If you follow those videos, if you did the activities I sent in the group, you'll be fine. More than fine. Right. See you on Wednesday. Also, from now on, we are not going to postpone any of our sessions. Right. I'll be feeding you with a lot of content. Right. I'm going on recess soon, so I'll have the time, right, to upload a lot of content, to record a lot of content. Right. So just make sure you go through it so that every time we have the session, right, I'm simply just addressing questions. Right. Make sure that when we have our sessions, you've already looked at the content, and I'm just addressing questions and maybe addressing maybe a few things that are left out of the content I would have uploaded. No, all the best, guys. Cheers.